Hey, good morning. Welcome to another exciting day of SE301. My name is Dr. Vikram Mittal, and I'm going to be teaching lesson 11 on cost analysis. So cost analysis is very important, and it makes a lot of sense because everything costs money, and normally you don't want to spend a lot of it. Cost analysis is the final block of solution design. And it makes a lot of sense that as you go through your different design alternatives and you generate a lot of different alternatives, each one's going to have a cost associated with it. In the next block, when we actually look at decision making, we'll look at the trade-off between cost and value, where, hey, you might have a solution that gives you a very high value, but it's also very expensive. And so you might scale back and go for a cheaper alternative that gives you a slightly lower value. But we'll talk about all that in decision making. Today's lesson is going to be broken into two blocks. The first is going to be about life cycle costs and time value of money. Second block is going to be about net present value. So here on the slide, you can see the definition from Parnell about life cycle cost. But the premise of life cycle cost is very simple. Over a system life cycle, you have different costs that you incur. As a systems engineer, you have to take into account all of those costs. So just for an example, over here we can see the system design process over system lifecycle, and from establishing the system need to retiring the system. Back when I was deployed to Afghanistan, I was tasked with redoing the walls at Camp Phoenix. And we were replacing like the traditional HESCO barrier wall with T-walls. So T-wall is a 18-foot concrete barrier. They're pretty large, they're pretty sturdy, and they end up costing about $2,000 a piece. So very expensive, and to surround our entire base, we needed over 1,000 of them. So somewhere in the ballpark of $2 million. We had the money, we got it approved. It was great, everything. And we forgot to take into account that there's costs that will incur after that. So whenever we had any sort of damage or any sort of attacks, we had to replace our T-wall, certain T-wall. So there was an operation cost associated with that. But what ended up really biting us in the end was the retirement cost. When we shut down Camp Phoenix, we had to do something with those T-walls because we didn't want other folks using our base for their purposes. So we ended up having to pay a contractor $1,100 per T-wall to destroy them. Yeah, so we didn't take into account the full system lifecycle because we left out the retirement cost. When you're looking at lifecycle costs, it's useful to be able to classify your different types of costs. So you can classify costs as being an acquisition cost, which is the total cost to procure, install, or put a system into operation. It's also useful to classify your costs as being either fixed or variable. A fixed cost remains constant regardless of quantity or lifecycle stage. A variable cost changes based on the level of activity. It's also useful to classify your costs as being either recurring or non-recurring. A recurring cost repeats with every unit of product, and it could be fixed or variable. A non-recurring cost is typically a one-time expense, and it normally happens initially when you're getting started. It's also useful to classify your costs as being either direct or indirect. A direct cost is directly related to a measurable activity or output, and an indirect cost is typically overhead. A great example for lifecycle cost is cars. So if you ever are looking to buy a car, a great website to go to is edmunds.com. And here you can see a screenshot of a 2018 Jeep Grand Cherokee. The sticker price is $43,000, but the true cost to own, according to this website, is $52,701. What do we mean by true cost to own? Well, we're looking at 5-year ownership. And the basic premise is, hey, we paid money up front, then the vehicle depreciates, and then we sell it at 5 years and recoup some of our money. So where does, in that, between the amount that it depreciates as well as the operation costs of the vehicle, that comes out to be $52,000. So the depreciation value is right around $21,000. Then you have taxes and fees, financing, fuel, insurance, repairs, and maintenance. Let's go forward a level and actually look at the year breakdown of that. So as you go through, you can see that certain costs on here are fairly fixed, like the fuel cost doesn't change that dramatically year to year, so that's a recurring cost, recurring fixed cost. Meanwhile, your maintenance cost up here is pretty variable, and you have a non-recurring cost right here of $2,100 for some sort of large maintenance work that's being done. Your insurance, again, is fixed and recurring. But what's interesting is you're looking at the life cycle cost profile, and down here you can see year one, you're spending almost $17,000, and then it drops down to about $8,000 to $9,000 per year to get you up to that $52,000 total over the course of 5 years. So over the course of each year, you spend a different amount of money, but now we have to look at the time aspect of money. So the economic value of money depends on when it is received, and the premise is very straightforward. If you have money in hand right now, you have the opportunity to invest it and get return on your investment. So it's better to have $100 now than having $100 a year from now. So if I have those $100 today, I can invest it 3% interest and have $103 a year from now. Meanwhile, if I am given $100 a year from now, that's the equivalent of being given $97 today, because I could invest that money and get interest on it to get to that $100 I'd have a year from now. So because of that, you have to take into account the time aspects of money. And when you're calculating out the time value of money, you normally use this notation that's shown on this slide. So you need 4 things. You need the interest rate, the compounding period, and then you have your present value of money, which is how much your money's worth today, and your future value, which is the money, how much your money's worth in the future. So your interest rate is normally given as a percentage, so 2%, 12%. Compounding periods, this is normally in years. Present value and future values in dollars. And the equations you use to convert between present and future value are given as being future value is equal present times 1 plus your interest rate raised to the compounding period. So working through a couple of examples, if you have $100 today, what is the future value 1 year from now if you invested in the SDP program? So future is equal to present times 1 plus I raised to the n. Your present value is $100. I is 10%, so 0.1. N is 1 year. So it's worth $110 a year from now. If you will have $100 a year from now, what is its present value today? Assuming 10% again. So we use the other equation, present equals future times 1 plus I to the negative n. And we get that it's $100 a year from now is equivalent of $90.91 today. So let's go through another example problem. Suppose I give you $5,000 today, using an interest rate of 3% accrued annually. How much do you have in the future after 1 year, 2 years, 3 years, and when does it become $10,000? So the interest earned in the time period, well, time period 0, you have no interest, so you have just your $5,000 initial investment. After 1 year, you multiply 5,000 times 1.03, and that gives you $150. That's your interest. So you add 5,000 and 150, and your investment becomes $5,150. Now you multiply that value by 1.03 and gives you an interest rate for your second year of 154.50. So that adds back into that 5,150 and gives you $5,304, and then you multiply that again by 1.03 and you get a little more money in your third year. And this kind of compounds over time and kind of keeps increasing as you go along. After 23 some odd years, you would have $10,000, so it would double. This kind of shows the compounding aspect of it and the importance of investing early So putting money into your retirement accounts at a young age, that way take advantage of what these compounding effects. So interest is important, but the other thing we have to take into account is inflation. And I'm sure all of y'all are familiar with inflation, but here's the definition from Investopedia for it. But the basic premise is that as you go further along, you end up having less buying power with your money. So if you look at the 1992 shopping cart versus the 1992 versus the 2012 shopping cart, you're getting significantly less. Or the example I like to give is when I was growing up, a McDonald's value meal was $2.99. Now $2.99 will get you next to nothing at McDonald's. So we need to, because inflation changes with time, and we know inflation rates and we can project inflation rates, we need to take that into account also with our time value of money. So the equations get modified just slightly when you're taking into account your inflation rate. So going with an example, suppose the interest rate is 10% and the inflation rate is 5%. What you do is that 1 plus I term becomes 1 plus your interest rate times 1 plus your inflation rate. So you have your 10% interest rate, 5% inflation rate, 1.1, 1.05, you multiply that together, 1.155. So that gives you what's called a discount rate of 15.5%. So effectively, this is effectively your interest rate going into your equations if you're calculating out present value or future values. A lot of times you'll see that discount rate and interest rate are used synonymously, and you do that because you're assuming no inflation. All right, so that wraps up the first block of lesson 11. Tune back in where we will talk about calculating out net present value.